Okay, today we will look at AIME 1996 and we will solve the 5 easiest problems. Let's start with the first one related to magic square. So it can be considered even as a problem for kids. It's like very simple math. There is a magic square here and it's called magic because the sum of numbers in any row is the same, in any column is exactly the same, and in any diagonal also exactly the same. So if you add up all the numbers in any row, in any column, or in any diagonal, you will always get the same result. That's why we call it magic square. And you are provided here 4 different numbers: x, 19, 96, and 1. Obviously, x is unknown, and you need to find x. Well, as simple as that. So, of course, when we try to find x in this problem, we need to use some reasonable approach. For example, if we try to write that the sum of numbers in this row and in this row are the same, it will give us simply nothing. However, so we should always understand what row and column should we use in each step. And here, for example, in the first step, we should use the first row and the first column. So let's write that the sum of numbers here, x plus 19 plus 96, equals the sum of numbers here, x plus 1 plus something. And something is the number here. And x obviously cancels out. And after that, this something that stays here should be equal 19 plus 96. It's 115 minus 1. So it's 114. 114 is a number here. Great. Next, if we, for example, again try to tell that the sum of numbers here and here are the same, you will not get anything appropriate, because once again you have 2 unknowns here. So the next step, which is the best to do, is to tell that the sum of numbers in this diagonal and, for example, in this row are the same, because here we have only 1 unknown. So let's mark it like this one, and 114 plus something plus 96 equals x plus 19 plus 96. Here 96 cancels out, and this something we can only express in terms of x, but good enough. So x plus 19 minus 114. Okay, so this something equals x minus 95. Okay, in this case, we will leave it like this, and we will rewrite this one as x minus 95. X minus 95 is the number that we have here. Well, the next step, what should we do? Obviously, here we have only 1 unknown in this row. Let's try to tell that the sum of numbers here is the same as the sum of numbers here. So x plus 19 plus 96 equals 1 plus x minus 95 plus something. So here x cancels out, and this something should be equal to 19 plus 96 minus 1 plus 95. Great. So let's look at this difference. This one is 95. 95 plus 95 is 190. So this sum is 190 plus 19 is 209. So this number is 209. Great. As you can see here, if you pay attention, you have several numbers here and only 1 unknown. Or for example here, you can use any of these columns. Let's use this one, or the third column. So we should write that 96 plus 209, 96 plus 209 plus something that is number here, equals, for example, again, the sum of numbers in the first row equals x plus 19 plus 96. And again, conveniently, 96 cancels out, and you have that this something equals x plus 19 minus 209. So this something equals x minus 190. Okay, x minus 190. And now you will have your final equation. So let me write it in the way that it fits this cell, so x minus 190. The final equation will look like this. You obviously, most of people probably understood what to do next. So the last equation, we should look at this diagonal, and we will tell that the sum of numbers in this diagonal, again, the same as the sum of numbers in the first row, for example. And it will provide you final equation for x, and it will allow you to find x. So the sum of numbers in this diagonal is x plus x minus 95 plus x minus 190 equals x plus 19 plus 96. Great. So immediately we can tell that 1x here and here cancels out. What we have on the left side? We have 2x minus 285 equals, and on the right side we have 115. Great. And it means that 2x equals, when we bring this number on the right side, it will be exactly 400, and eventually x equals 200. And it is the right answer for this problem. So this number must be exactly 200. This is it. Let's go to the next one. Okay, the next one that we solve today is number 2, and if you pay attention at this one, you will quickly figure out that it is a very light, very simple version of similar problem from AIME 1994. So, and when we solved the previous one, we learned a very simple fact that if you want to look at this number, for example, floor of log 2n, the best way to do it is to consider that n is always between two consecutive powers of 2. Really, so there exists some interval with the left end 2k and with the right end 2k plus 1. So this end included, this one is not included, that n belongs to this interval. And after that, we figured out that log 2n is this power of 2 that is on the left end of this interval. So we'll explain now why it happens. I will just remind. So the idea is super simple, that you want this logarithm to be a normal number. Well, it is a normal number in general only if n is a power of 2. Well, in order to assess this one, we will simply divide numerical line into intervals where the end of the intervals are powers of 2. For example, instead of 1, we write 2 to the power of 0. Instead of 2, 2 to the power of 1. Instead of 4, 2 to the power of 2. Instead of 8, 2 to the power of 3, and so on. So we divide a numerical line in this way, and we will consider these intervals that do not intersect. So the left end will be included. Right end is not included. We don't want them to intersect. That's why the structure will be like this. For any interval, left end included and right end is not included. And of course, if you take any positive number n that is greater than 1, it falls into one of these intervals right here, and you can write inequality that n belongs to this interval, and therefore n is less than 2 to some power of k that is on the right end of this interval, and greater or equal than 2 to the power of k that is on the left side of this interval. Very simple. And now the only thing that you need to do is to take log 2 from all sides. So we take log 2, and here instead of 2 to the power of k we'll have k, here we will have log 2n, and here we will have k plus 1, and it means that the number log 2n is in the interval where with the left end k and right end k plus 1. So it is an interval of length 1. K is included, k plus 1 is not included. And in this case, what would be log 2n? The largest integer on the left of this number, obviously it is k, so it should be equal to k. And that's how this assessment, that's where this assessment comes from. And the next thing that we learned in the previous problem is very simple. If you have an interval ab and both ab are integer numbers, how many other integers do you have in this interval? Obviously it's b minus a. Well, as simple as that. It's just you can check it yourself. Very simple assertion. In particular, for any interval 2 to the power of k, 2 to the power of k plus 1, how many integers do we have in this interval? From 2 to the power of k included and 2 to the power of k plus 1 not included. In this case, it will look like 2 to the power of k plus 1 minus 2 to the power of k, and because of powers of 2, it simply equals 2 to the power of k. Well, very simple. This is it, and that's the only thing we need to know to quickly solve this problem. What we have here, they explain you at first what is the floor of x, so thank you very much, and then they tell for how many positive integers n we have n is less than 1000 and floor of log 2n is a positive even integer. Well, we already figured out that if we want to consider this floor, then we should consider between which powers of 2 we have our number n. And then this log is simply a power of 2 that is on the left of n. This is it. And therefore, let's divide like numbers between 1 and 1000 into segments. And the end of the segments are powers of 2. So we'll start here, we'll just mark 0, 1, which is 2 to the power of 0, 2 to the power of 1, here we have 2 to the power of 2, here we have 2 to the power of 3, and so on, and up to 1000. So 1000 is close to 2 to the power of 10. So here we will have 2 to the power of 10, and it will be 1024, and 1000 will be here. So this last interval from 2 to the power of 9 to 2 to the power of 10, it's like not completely in our range. Nevertheless, so let's just quickly consider what we have, for example, if n belongs to this first interval. Well, it's not even an interval because it's from 0 to 1. So this one is not included because here we only consider n that positive integers n, and this one, this logarithm, also has to be positive even integer, and n has to be an integer. There are no integers from 0 to 1. From 1 to 2 also we have no integers. From 2 to 4, well, we have exactly 2 integers here, 2 and 3. And for each of these integers, what we have, for example, here if n is in this interval, the log 2n, floor of it, is the power of 2 that is on the left end of this interval. So it equals 1. So log 2n equals 1 for any n from this interval. However, 1 is an odd number, and we are looking only if it's a positive even integer. So odd, but we need even. Doesn't work for us. Obviously, the next one will work for us. If we look at the interval from 2 to the power of 2 to 2 to the power of 3, if we take any n from here, then log 2n floor is simply 2. And it means that for any n from this interval, it works for us. And how many possible values of n do we have in this interval? Well, we don't even need to think about it. We already know for any interval with like these ends or these ends, the amount of integers in this interval is 2 to the power of k, and in general it's b minus a. So the total number of integers n here is 2 to the power of 3 minus 2 to the power of 2. This interval works for us. The next interval from 2 to the power of 3 to 2 to the power of 4 will not work for us. The next interval from 2 to the power of 4 to 2 to the power of 5 will work for us, because for any n from this interval, log 2n will be equal 4, which is a even integer number. So, and let's write from 2 to the power of 4 to 2 to the power of 5. For any n from this interval, it works for us. And how many integers n do we have here? Obviously, the result is 2 to the power of 5 minus 2 to the power of 4. The next interval from 2 to the power of 5 to 2 to the power of 6 doesn't work for us. The next interval from 2 to the power of 6 to 2 to the power of 7 works for us. For any n from this interval, we have that log 2n simply equals 6. And here it was 5, so it works. So how many integers n do we have here? 2 to the power of 7 minus 2 to the power of 6. Then the next interval from 2 to the power of 7 to 2 to the power of 8 doesn't work for us, because here we have this value equals 7. And 2 to the power of 8 to 2 to the power of 9, it worked for us. So it means that here we have 2 to the power of 9 minus 2 to the power of 8 possible values of n. And finally, 2 to the power of 9 is already 512. From 2 to the power of 9, from 512, we would like to write up to 1024, up to 2 to the power of 10. But it's not in our interval. We're only interested in n that are like less than 1000. So if they are less than 1000, then here we write 1000, and 1000 can't be even included because it's strictly less than 1000. It's just by the condition of our problem. And if you take any n from here, you will see that this one is a power of 2 that is on the left end of this interval, which is 9, which is odd, doesn't work for us. So only several intervals worked for us, and for each interval we have that numbers of this amount of n that work for us. So, and of course, by the property of the power of 2 here, we can simplify our calculations. And for example, in this case, this difference is 2 to the power of 2, this difference is 2 to the power of 4, this difference is 2 to the power of 6, and this difference is 2 to the power of 8. And that's how many values of n in total we have that work for us. And let's add these numbers. So this one is 4, this one is 16, this one is 64, and this one is 256. And in order to add these numbers in a normal way, let's do it in a reasonable manner. So this one will be added to this one, because in this case we will get 260, good number, and this one will be added to this one. In this case we will have 80. So 260 plus 80, and totally we have 340 different values of integer n that are less than 1000, and for each of these n we have that log 2n is a positive even integer. So 340 is our correct answer. This is it. Let's go to the next one. Okay, let's solve number 3. It's a very short and pretty simple problem. So find the smallest positive integer n for which, if you expand this expression and you add like terms, at the end you will have 1996 different terms after expansion. So but you need to find the smallest positive integer n for which, if you expand all of that and you add like terms, eventually you will end up with 1996 different terms, at least 1996, maybe more. Great. So the question is very simple, and if it's not very clear how to solve it from the beginning, at least you can pay attention at this expression, and you can see here that you have 3, 7, and 21 is 3 times 7, and it is a great hint for you that maybe you can factorize this expression. Let's look at this one, and maybe, let me just try to write it, maybe x minus 3 times y plus 7. Will it work? X, 7x, so this one will not work. However, we will not give up. Let's try like this. So it will be x plus 7, y minus 3. Will it work? Yx, 7y minus 3x minus 20y. Works perfectly. So this expression is exactly as this one to the power of n. Okay, and if you raise this one to the power of n, it will be exactly as y minus 3 to the power of n times x plus 7 to the power of n. And well, now it looks way better than this one, because this one was pretty intimidating, and in this form it's way better. What do we know about this expression? For example, something y minus something to the power of n. Well, we definitely know that it looks like this. It will be y to the power of n plus something times y to the power of n minus 1 plus something times y to the power of n minus 2 plus and so on, and eventually plus something times y plus some number, and in this case it will be like plus 3 to the power of n, maybe with a plus sign, maybe with a minus. We just don't care about the numbers. You can of course remember binomial theorem. It's just not about it. It's just about the general way how it looks. So you will have here powers of y plus or minus some number at the end. This is it. And how many terms you have here? How many terms? Well, you have exactly n different powers of y plus one number. So you have here n plus one term. And the same here. If you expand this one, you will have x to the power of n plus something times x to the power of n minus 1 plus something times x to the power of n minus 2 and so on, plus something times x plus 7 to the power of n. Great. Again, so we don't care about the signs, we just care about how many terms do we have here. And here again, we have exactly n plus 1 term. Eventually, when you multiply this one by this one, what will you have at the end? So let's just imagine that we multiply this one by this one. We start with y to the power of n, and we will multiply it by this one, by this one, by this one. And how many terms will we have eventually when we multiply this one by all of this? Obviously, we will have n plus 1 different terms after multiplication of this one. Okay, if we multiply, go to the next one, and of course, we expand, so we have to multiply this one by all of these. We will have again n plus 1 different terms after multiplication. Very important that when I multiply y to the power of n by any of these terms, I have expressions that look like y to the power of n times something, and when I multiply this by any of these terms, I get an expression that looks like y to the power of n minus 1 times something. Obviously, you can see here that these are not like terms. These are not like terms. After expansion, you will not be able to just add them because you have different powers of y here. So here you will have, after multiplication, n plus 1 terms, and here also n plus 1 terms, and these are not like terms. So it means that you will have n plus 1 from multiplication of this one, plus n plus 1 from multiplication of this one, plus n plus 1 from multiplication of the next one, y to the power of n minus 2. And again, when we multiply this one by any of these, you will have n plus 1 terms, and none of them is like to any of these, because you have different powers of y. You will not be able to add them. And so on. Eventually, you go up to this one, so n plus 1, and how many y do we have here? We have here exactly n different powers of y, and now we go to this number, and we will also multiply it by each of these terms here, and again we will have n plus 1 different terms, and none of these terms, when we multiply this number by any of these, is similar, is a like term to any of these, because here we simply have no powers of y, and here we have powers of y, so you can't add all of that. And here also one additional time. So you add up n plus 1 times. So you add up n plus 1 times, and the result is n plus 1 squared. So it means that after expansion of this expression, so after expansion, you will get exactly n plus 1 square different terms. This is a very simple conclusion. If you expand all of that, we got that eventually you will get n plus 1 different terms. And you need that n plus 1 squared should be greater or equal than 1996, because the requirement is that the amount of terms should be at least 1996. Well, let's solve this one. N squared plus 2n plus 1 greater or equal 1996. I just get 1 here, and it will be 1995. N squared plus 2n minus 1995 greater or equal than 0, and eventually you can work with this one. You know, I think that this approach that I did here is not the best one, because here you will have to solve a quadratic equation. You will have to go to discriminant, and it will be just a waste of time for us. What if we look at this expression right away in a very simple manner? Square of some number is greater or equal than 1996. Well, what should be this number? Obviously, if you work with like 44, it's just approximate, because I know that 45 square is more than 2000, and 44 is probably less than 2000. So let's quickly calculate these squares, and we will make an assessment about this number. So 44 times 44, 6. It will be 16, 1 is here, 17, this one 16, 1 is here, so 17, 6, 3, 1, 9, okay, 1936. So if this n plus 1, if this is 44, it doesn't work for us. If n plus 1 is 44, this square is 1936, and this inequality is not true. So 44 is not an option, and we can even delete it. But what about 45? Well, 45 times 45 is 5. Here you have 22, 0, 2, 18. So it will be 5, 2, 0, 2, 2025. So, and it means that 45, this n plus 1, when it's 45, it is the first and the smallest number that will work for you, because only for 35, it is the smallest number for which the square is greater than equal than 1996. So n plus 1 must be exactly 45 if we are looking for the smallest value of n. And in this case, n should be equal to 44. That's the reasonable approach how to solve this problem, and it is the right answer. So this is it. Let's go to the next one. Okay, let's go to the number 4. It is a geometry, and a wooden cube whose edges are 1 centimeter long rests on a horizontal surface. So immediately when you read something like this, it makes a lot of sense to draw a cube. And after that, you will mark some other conditions just along the way. So we will draw a cube. So I will not promise you to draw a perfect cube. I love geometry, but my hand is pretty weak on drawing, so that's not my story. I'm not very good at this one, but I will try to draw something that looks like a cube, and we will be good to go. Perfect. Okay. Perfect cube here. A wooden cube whose edges are 1 centimeter long rests on a horizontal surface, and the surface will be somewhere here. So it's plane, and the cube is standing on this plane, and illuminated by a point source that is x centimeters directly above an upper vertex. Well, directly above, it means like this. So some edge should be extended. Well, let's extend, for example, edge that is like far from us. This one, we extend it, and this one is x centimeters long, and there is a light point source. When someone tells you that there is a light point source, it means that it emits the light in all the directions, like everywhere. And vertex, the cube casts a shadow on a horizontal surface. Okay, so if the light source is here, it emits the light in every direction. What would be the form of the shadow? Very simple and very obvious question. Obviously, there will be no shadow like on this side and behind the cube, because light source is here. It emits light in every direction. There will be no light here, no shadow here, and the only shadow that we will have from this light source will look like this. You should connect this light source with the vertices of the cube, and these rays will show you that the shadow will be like this. So this one will be exactly along diagonal of the cube. So I will redraw something here, and this one will be also along this line of the cube. So, and let me make like a better picture here. You obviously understand how it will work out. So this one with this one is a part of the shadow, so it's 1 point. Another point will be here. We will explain why shadow looks like this, but let's make some drawing here. Okay, perfect. And this is it. So it will be a part of the shadow that you see here. So this one is a part of your shadow that is produced by a cube. And of course, you will have exactly the same shadow on the other side, because the situation is completely symmetrical. So let me connect this one, and after that, this one. Well, obviously, our suspicion here is that this is trapezium, and this is also a trapezium. Why the shadow looks like this? Well, at first, there is no shadow on the other side. We already discussed it. And if the light source is located here, obviously, the edge of the shadow will be the image of this edge. The image is formed that you connect this point with every point on this edge. And so after that, this line should intersect the plane on the bottom, and you will have here a segment, because why will you have here a segment? Very simple. If you make like a plane through these 3 segments, this plane will be like this, and it will intersect 2 parallel planes that passes through this face of the cube and this face of the cube. And this plane intersects 2 parallel planes, and intersection will be 2 parallel lines. So this line is parallel to this line, and because this line is parallel to this line is parallel to this line, and therefore this is a trapezium. And it's very easy to understand what is the form of the shadow. Obviously, you can also understand that, for example, this ray will intersect the bottom plane at the point that is like in the same plane with this line. So it's just the basics of stereometry. After you look at the picture, you will quickly understand that this is a trapezium, and it is exactly the same trapezium. And when they tell us that the cube casts a shadow, this is the shadow. It's exactly 2 trapeziums. And the area of the shadow, which doesn't include the area beneath the cube, so this area on the bottom is not included for us, is 48 square centimeters. So the total area like this is 48 square centimeters. It means that the area of each trapezium is 24 square centimeters. And find the greatest integer that doesn't exceed 1000x. In other words, you need to find x, and after that we will figure out what to do next. So let's look at this problem. It looks pretty simple because the edges of the cube are 1, 1, 1, 1, 1. And here you have a lot of similar triangles. For example, this triangle is similar to this triangle, or this triangle, like this right triangle, this angle is 90 degrees, is obviously similar to this triangle because these are parallel lines, or this triangle is similar to this triangle because, once again, right triangles and this angle equals to this angle. So we have a lot of similar triangles, and we will go in this direction. For example, this triangle is similar to this one, and it will allow me to find this this side. Okay, so how can I find this one? Let's make it y. And for example, from similarity of these triangles, we can write that this leg over this leg, which is simply a tangent of this angle, so x over 1 equals the tangent of this angle 1 over y. Well, again, or you can use similarity of triangles or tangent, just doesn't matter. So from here, y equals 1 over x. So this y is simply 1 over x. Let's write it here. So 1 over x. And what is this lateral side of trapezium? Obviously, if you extend an edge of the cube, this one is 90 degrees, this one is 90 degrees, and this line is parallel to this line. This is a second, so this is also 90 degrees. So this is the height of your trapezium, and these are the bases. So it's like an altitude, and it equals 1 over x. Once we are talking here about the area of trapezium 24, we remember the formula. It's the half sum of the bases times this height. So one base of this trapezium is 1, and we obviously are left with this base. If we find it, we will simply make an equation that will allow us to find x. So, and if you want to find this base, you should consider this triangle and this triangle. They're similar. And what do we know here? Well, for example, we know that this one is simply 1, so this side is 1. This side is, we will denote it as y. We can still use the same variable here, y. So now we can only tell like 1 over y equals, and we have no idea what it equals to. This one divided by this one. Ideally, we would like to write that it is equal this side divided by this side. And we need to express, because at the moment we have no idea what is this one, but from this right triangle on here, we have that this one is 1 plus x squared. It's very simple to get from Pythagorean theorem. From this right triangle, this side is 1 plus 1 over x, and again squared, like this. So let's write now that this one is 1 plus x squared divided by this side in total. It is equal to square of 1 plus x squared, so this part plus this part, plus square of 1 plus 1 over x squared. Great, that's what we have. And after that, we can here express y. So y equals 1 plus x squared plus 1 plus 1x squared, I already squared all of that, and divided by this one, it will be 1 plus x squared. Well, in general, when you look at this expression, it's very easy to simplify. At first, I can divide it like this one by this one plus this one by this one. So it will be 1 plus this one, this square root, 1 plus 1x squared, divided by 1 plus x squared. Great. And if you add 1 and 1 over x squared, you will quickly realize that here you will have 1 plus x squared, and x squared will be on the bottom here, and here you will have 1 plus x squared. So this line doesn't extend here, so this is it. And this expression is simply 1 over x. So if you divide it, you will get square root of 1 over x squared, and it will be 1 over x. So the total value is 1 plus 1 over x. And we can again write it as x plus 1 over x. This is it. So we got that this value of y is actually x plus 1 over x. X plus 1 over x. Great. So finally, we are ready to write the final equation. The area of this trapezium is 24. So the half sum of the bases is 1 plus x plus 1 over x. I'm sorry, x plus 1 over x. All of that divided by 2 times the height times 1 over x equals 24. Let's solve this equation and we will try to find x. So from here, we multiply both sides by 2 and we will get 1 plus x over x times 1 over x equals 48. So here, when we add all of that, we will get 2x plus 1 over x squared equals 48, and here 48x squared minus 2x minus 1 equals 0. Let's try to solve this equation. We will see, maybe we'll get some normal solution. Discriminant equals 4 plus 4 times 48. 4 times 48 is 192. And it is equal to 196, which is 14 square. Amazing. If you get discriminant like this, it means that you are on the right track. So it means that square root of discriminant is 14, and the solution is x equals minus this one, it will be 2 plus minus 14 divided by 2 times 48 equals 96. And obviously, the negative value of x doesn't work for us. The only thing that works is 16 over 96, and it is simply 1 over 6. So we found out exactly that the precise value of x is 1 over 6. So x is 1 over 6. Let's look at the question, what they ask us here. Find the greatest integer that doesn't exceed 1000x. Okay, so the greatest integer that doesn't exceed 1000x. So 1000x equals 1000 divided by 6. Let's divide it. Well, we can do it like in a regular way. Divided by 6. 1 minus 6. 40, 6 minus 36, it will be 40, it will be 166. Yeah, 166, and what is the remainder? 4. So I can write it 1000 divided by 6 equals 166, and the remainder 4, and 4, 6. It will be like this. 166 and 4, 6. 166 is an integer result and 4 is a remainder. And you need to find the greatest integer that doesn't exceed 1000x. What is the greatest integer that doesn't exceed this number? Obviously, it's 166. 166 is our answer for this problem, and it is a correct answer. So let's go to the next problem. Okay, we have our last problem, problem number 5 for today, and we solve it and we are good to go. So suppose that the roots of this equation are a, b, and c. So, and as you can see, it's a normal equation that we used to see, that we used to solve. And the roots of this equation, and this already an equation with these coefficients, which are variables, r, s, t variables, they are like not defined. But we know that this equation has roots that look like a plus b, b plus c, and c plus a. You need to find parameter t. So t is a free coefficient here. So let's just go step by step. When you have these problems, it's very important to start from the beginning and to try to get some information when you read just from the beginning of the problem. So you get just information, and step by step it will lead you to the solution. So we'll start from the simplest part. This is an equation that is a normal one, and a, b, and c are roots of this equation. Well, immediately you can tell that in this case x cubed plus 3x squared plus 4x minus 11 can be represented as x minus a, x minus first root, x minus b, x minus second root, and x minus c. So this representation is possible. All the coefficients here on the left side are well known. What is this free coefficient 11? If we multiply these expressions, what would be our free coefficient? Well, the only thing that will not contain x is when we multiply this one by this one and this one by this one. So it will be minus ABC is on this side, free coefficient, and it should be exactly the same as a free coefficient on the left side. So it should be equal minus 11, and therefore ABC equals 11. Great, it is our first result. Let's go to the next step. Coefficient near x, you have 4. How to get here coefficient near x? Just we want to quickly understand what will it be. If you multiply x here and you want this x to be without any powers, it will be multiplied by this one, and then x minus b minus xb, this product, should be multiplied by minus c. So the result will be, will look like this. It will be cbx. But also you can multiply this x by these two, and it will be plus acx. And also you can multiply this x by these two, and it will be abx. So the coefficient near x on the right side will look like AB plus AC plus BC, and this coefficient on the right side should be exactly as you have on the left side, so it should be 4. It is our second condition from this. And eventually we also can write that we have a coefficient near x squared, and it should be equal to 3. So it doesn't matter to go to x cubed, because if you multiply here these numbers, the only term where you have x cubed will be x times x times x, it will be x cubed, and here you have x cubed. So you will not get any additional information, but with x squared, you can understand here what would be the coefficient near x squared. You should multiply this one by this one, and then by minus c. So it should be minus cx squared. Then, for example, this one by this one, it will be x squared, and then by minus a x squared, and eventually the last one will be minus bx squared. So the coefficient near x squared should be minus a minus b minus c times x squared, and this coefficient should be exactly equal to 3. So this should be equal to 3. It means that a plus b plus c should be equal to minus 3. Let's sum up what information could we get from our first condition. So this is first. Another thing that we have here is ab plus AC plus BC equals 4. That's what we have. And ABC is 11. ABC equals 11. That's what can we get from the condition that this equation has roots ABC. This is it, nothing more. It is like the maximum that we can get from it. So now we have this equation, and it has roots a plus b, b plus c, and c plus a. Well, let's use the same approach. If this equation has these roots, then it can be represented as the similar product. So let me write this equation: x cubed plus rs squared plus rs squared. So in order for us to save time, we will just write it like this: x cubed plus t. We will not write all this equation, but it can be represented in the next way: x minus first root, x minus a plus b, then x minus b plus c, and then x minus c plus a, x minus c plus a. Pay attention that here in this expression, we need to find only t, so we need only free coefficient. And as we figured out here, for example, here free coefficient 11 was exactly the product of a, b, and c, because only the product of a, b, and c here, when you multiply, it will not contain any x's. But here you have exactly the same situation. When you expand here and you will equate the left and the right side, you will tell that everything here on the right side, for example, that stays near x, should be exactly the same as on the right side near x, and the same for the free coefficient. So the free coefficient from the right side should be a product of these three elements. And it means that this free coefficient t must be equal minus a plus b times minus b plus c times minus c plus a. Eventually it will be minus a plus b times b plus c times c plus a. Well, and here obviously we have already some conditions to a, b, and c, right? And maybe if we use some reasonable approach, by using these conditions, we will be able to find what is this value, and we will be able to find t. That's the main idea. So here, the best approach is simply to multiply. So it will be minus a plus b times b plus c. It will be ab plus ac plus b squared plus bc. Okay, and times c plus a. Eventually, let's do our final step, abc plus a squared b plus ac squared plus a squared c plus b squared c plus b squared a plus bc squared plus abc. Great, and here, if you want to group summands here in a reasonable way, so you will pretty much understand how it really looks. The best way to do it like this. So at first we go with ABC, so it is a like terms, so it will be 2ABC, and then you see what we have here, a squared b, b squared a. So let's make it a squared b plus b squared a plus a squared c plus c squared a plus b squared c plus c squared b, and it will look like this. See what we have here. Okay, so 2abc, no question about it, it is simply 22. So it will be minus this 22 plus this sum that we have here. And we would like to find this sum, and obviously we need to use these conditions. And this, for example, if we try to factorize here ab, we will have a plus b. Here we can factorize ac, we will have a plus c. And it doesn't look like there is a good option to factorize all of that by, for example, factoring out something out of these two, But as you can see here, a squared b, and it maybe you can look at these expressions and you will get a squared b, for example, if you multiply this one by this one, and you will get b squared a if you also multiply this one by this one, really b squared a, and you will get a squared c if you multiply this one by this one, and b squared c if you multiply this one by this one. So, and it is a hint for you that if you multiply these two expressions here, you will get every term that is present here. So maybe let's multiply them independently here, and we will see what we get. For example, if we multiply a plus b plus c, we will multiply it by ab plus AC plus BC. And it's obviously we know that one is minus 3, another is 4, so it is equal to minus 12. So we'll keep it in mind. And what would be this product? Let's simplify the process, and we will not expand it like in a long way like we did here. We will understand right away how the process will end. Obviously here, when you multiply all of that, you will have all these terms, a squared b plus b squared a plus a squared c plus c squared a plus b squared c plus c squared b. And besides these terms, what else will you have? Well, you will have only the terms that look like a, b, c. For example, a times bc is one abc, b times ac is another abc, as c times ab is another abc. So eventually you will have here plus 3abc. Okay, so let's look here. On this side we have minus 12. On this side we have the needed sum, the sum that we are looking for. Here we have 3abc, and 3abc is simply 33. So instead of this one, we can write here 33, and this needed sum is minus 12 minus 33. So this sum that we are looking for equals minus 12 minus 33 equals minus 45 minus 45. So this sum is minus 45, and here we have minus 22 minus 45, and it equals to, here we have minus 23, and minus 23 is simply 23. And therefore, the value of this expression is simply 23, and the coefficient t that we are looking for, it should be equal to 23. And it is a correct answer for this problem. This is it. So we are done for today. Thank you.